All right, here it is. I don't know if I can be any clearer than what's on here. This reaction, oxidation of a secondary alcohol to a ketone, will be on your test number 4. It was not on test 4, fall 21. It is a critically important reaction that you use on every test in Chem 242. Every test, no exceptions. Okay? So we have to learn it now because it's so important. And we studied it on Monday, which means you guys haven't reviewed it yet, I know. But here it is. The first thing you have to do is activate the chromanyl. Chromanyl is like carbonyl, but chromium's there. So which of the bonds to oxygens are chromanyl? Chromanyl is like carbonyl. Which the double bonds. Don't protonate the single bonds to O. That doesn't happen. You need to pick a bond that can resonate. Make a bond that can resonate. You're attacking the strong acid catalyst. The catalyst gets used, I think, 3 times. This is the first. This is the first time it's used, and then there'll be a regeneration. That cycle will be about 3 times. So you got an activated chromium. Draw it under your alcohol. I protonated the top one. It's a chromanyl oxonium now. Put a lone pair on the oxygen of the alcohol. It now attacks the chromium and breaks the pi. Green arrows. So we need a little room down here. Here's our skeleton. Here's our O with an H. And we made hydrogen sulfate. You got a bond to chromium here. It has a double bond on the bottom. I don't know why I made all these black. The only thing I wanted black was the new H. So I still have an OH to the left and an OH to the right, and we have a new OH on top. And plus charge. That's an oxonium. Strong acid needs to be neutralized. Neutralize it. Yeah, I did it again. That needs to become this. Something that looks like chromic acid again. With 2 double bonds to O, like the very beginning. And an OH on the right, not an OH on the left, it's an OC, that's an ester. The H from chromic acid has been replaced by a C. That's called an ester. That's true for every ester. You take the H off of an ic acid and put a C in its place. You now have an ester. This is how esters are made. We got to make this thing lose water. You need the same catalyst you've used. You used it for 1 cycle. You started it here, you regenerated it here. You need to start it again over here with the base grabbing an H and the acid providing an H. It looks a lot like tautomerization. It really is called elimination because you're making a pi, right? And that's it. That's dehydration right there. And you're almost done. You got to remember, you need to make a chromate ester. Then you're going to ask yourself, how do I know what a chromate ester looks like? I'll say it again. It looks exactly like chromic acid. You take the H off of an ic acid and put a carbon in its place, and you have an ester. So if you don't know what you're drawing, then you didn't listen. Okay? I need to have a chromate ester, even if the teacher didn't draw it for me. So you have to know what they look like. You're getting a point for it, even if you don't do the mechanism right. So this O ends up in the chromate ester attached to chromium. And you got to realize which atom is being lost from the carbon skeleton here to get to the same carbon skeleton here. So which atom is lost from this carbon skeleton to get to this carbon skeleton? There's an atom missing from this skeleton that was on this one down, right down here. There's a hydrogen down there. Sometimes people miss reactions because the stick figures are oversimplifying in their brain. Yes, we deal with those H's in stick figures. When we need them, we draw them. And there's an H here that isn't there in the products. It ends up as part of hydronium. And you know, you've got water here. You just made water. You want it to be with the same color scheme. It's a green HO and a black H that needs to become hydronium. How do I know? There's a hydronium here. We haven't made a single hydronium yet. So talk to me. Which color H are you going to grab with that lone pair? The blue. What are you going to do with the sigma bond? Make it into a pi. There's a lot of that going on, isn't there? Yeah, we did it here. Sigma, grab H, make pi. Earlier today, we did a couple more. There's a name for this kind of reaction. I don't know why my reaction arrow suddenly became blue. Oh, because I was talking about the color blue. There we go. Hey, make a pi. What kind of reactions make pi? It's another elimination. Although they don't call this an elimination because carbon's oxidation state changed. They call it an oxidation. But guys, in your brain, you think elimination, and you're helping yourself with this mechanism. I know it's a little big. You've done bigger. And you know this one, just like the hydroboration one and oxidation, which you guys are pretty good at now. When you know it's coming, you're ready for it, right? Same story here, and you know this one's coming over and over. Never going to stop. Okay? So, very important mechanism. I'll talk about why I didn't mention it this morning, because in truth, I thought it was already on the test this morning. Okay? That was wrong. So my apologies. I didn't look carefully enough, but I think we covered it. So there will be no fuzzy memories of it being on the test. We know it's on the test.